part of this today's session, which is Rom cells. So we talked about Rom cells earlier. What was one thing that we established for the Rom cells when we were discussing Rom cells earlier?
So we were using different kind of layers like the diffusion or the metal or the via to program them.
Mm-hmm. And what did we establish?
So that higher the metal layer, better the time to market.
The higher the layer at which I do the programming, faster is the time to market, and therefore I prefer to do all my programmation at higher levels. At that point of time, there was a question about how do we program, and that is what we are looking at now. Okay, so let us say this is a memory, this is an array of devices where this is one row, this is another row, another word line, and there are all these NMOSs that are kept. The vertical purple lines are bit lines. Okay, but do you notice the bit lines are the memory cells are not connected to the bit lines yet? Are you able to see that?
Yes, sir.
So what we do is we say that wherever I want to write a 0, that is wherever I want to discharge the bit line, at that place I will connect the transistor to the memory, to the bit line. At other places I will not. So what happens? This one would discharge, this one would not. Now the challenge is that there are some bit lines where there is, say, X number of connections. There are some bit lines where there are no connections. And there are some bit lines where every NMOS cell is connected to the bit line. Are you able to see this?
Yes, sir.
So do you want this kind of a situation for your bit lines, or do you prefer something else?
So what is the challenge?
First, have we understood what is the programmation being done here? How is the programmation being done here? Any questions about the programmation part?
So I'm not able to understand that.
So contact means writing 0.
Yeah, if I connect it to the bit line, I'm saying that I'm writing 0 there. The bit line would discharge. If I'm not connecting, then when the word line goes on, the bit line would not discharge. So I've kind of programmed that cell to 1.
Right. Yes.
Okay. So we are doing that programmation, and over here, what we are doing is some bit line, we are either connecting the bit line to the transistor or not connecting it to the transistor.
Sir, I had a doubt, sir. In the first column and the second column. In the first column, only the upper transistor is connected to the bit line. In the second column, both the transistors. So, but discharging would be taking place in both the bit lines. So, like, how will I distinguish this?
Okay, tell me one thing. When I select word line 0, let us say the bottom one is word line 0 and top one is word line 1. What will I read? Word line 0 पे अगर select करा तो?
Yes. Yes, sir. Yeah.
1 0 1 0 1 0 1 0. If word line 1 was selected, what would I read?
So above 0 0 0 1. Yeah.
So that is how we have programmed the memory there.
Yeah. Yes.
Okay. Now the problem is that over here every bit line has different capacitance. Every bit line has different capacitance. So how will you size your pre-charge circuit? How will you size your right driver circuit? Here's some columns, right driver, so there is no right driver in a ROM, but pre-charge is there. So some columns will get pre-charged very fast, others will not get pre-charged fast. Some columns will discharge very fast, others will not discharge fast. Let us say these two, let us consider these two columns. Okay. In these two columns, this has very high load on the bit line. This bit line is not that high. Suppose, let us consider two columns. In one column, say 90 cells are connected to the to the bit line, 10 are not. In the other one, let us say 10 cells are connected to the bit line. Now, I want to read a particular row where this cell is connected, but this is not. So what happens? This bit line will discharge to 0 very, very fast because the bit line capacitance is low. This bit line will remain at VDD. However, because its load is very large and there is so much leakage on it, it will fall a little. Okay. But there is this very fast moving another signal right next to it. It will cause it to fall further due to coupling. Okay. So we do not really want such kind of, you can actually analyze your design and you can arrive at what is the worst case for which you need to design. But the reality is on silicon, then there will still be many variations, many race conditions that will be there. We want to avoid that. If we want to avoid that, the same NOR cell, we program it differently now. What we say is all the NMOSs are now connected to the bit line. What do I program? I program the connection to the ground. So I am connecting some things to the ground, others there is no current path. So it is 0, 0, 1, 0, 1, 1, 0, 0 on the top row, and 1, 0, 1, 1, 0, 1, 1, 0 on the bottom row. But over here, the benefit is that the capacitance of all the bit lines is same. Are you able to see this? Any questions?
Sir, for example, in the earlier case, when we were contacting with the drain region. So in that case also, like with the worst case kind of that, we can basically design a circuitry, the circuit such that only after that time only the signals will be generated.
Yeah, we can do that. I agree, Raghav. But it's still, while I can design the worst case, on silicon, I want as much symmetry and as much control as is possible.
Yeah.
With so many bit lines varying at different rates, it will be very difficult to debug if there is a failure on silicon. There are so many additional variables. Now, what is the capacitance? What was the code that was written? Because every chip will have a different code.
Yes, sir. Well, yeah, yes, sir.
You see, every chip will have a different code. So the number of variables that you have to handle in silicon debug, they increase overwhelmingly. You want to keep much more control with yourself. So you say bitline capacitance we maintain to be the same. Only the source side we now do the programmation.
Yes, sir. Yeah.
Okay.
Sir.
Yes.
Sir, previously we were programming it towards the drain position, right? Sir,
Yes.
so, sir, I didn't understand how the load is changing, sir, exactly on a bit line.
Okay, on a bit line, you have 10 source or drain regions connected, or you have 5 source or drain regions connected. Will the load change?
10 source or drain regions, 5 source. I mean, okay. So, sir, what I understood about load is that there would be a capacitance corresponding to the drain position of the transistor. That
Is there, wait, Vaishnav, is there a capacitance that is related to the drain and source region of a memory of a NMOS?
Yes, sir. In DVD, we have studied about that. Yes.
What is that capacitance?
Value is Kc. I mean, K into C.
No. We did something more also. We looked at the sidewall capacitance and the bottom capacitance.
Yes, sir. Yeah. Yes.
So there is a junction capacitance that comes into picture. Whenever you connect any source or drain region to any particular signal, that signal gets loaded because of the junction capacitance.
Yes, sir.
So the more the connections to the source and drain, the more the capacitance. The lesser the number of connections, lesser the capacitance.
Okay. So, sir, how did we overcome this that issue in this source connection, sir? While we are
You tell me. look at any bit line, how many source regions are connected to it? How many how many transistor drains are connected to it? Is it changing across bit lines?
Oh, got it. Understood. Yes, yes. Yes, got it.
Okay.
Yes, thank you, sir.
Yeah. So this is the NOR cell. And NOR cell, what we are doing is we are selecting all the cells, and we are selecting the cells, and wherever there is a what do you say, 0 written or a 1 written, depending on that, the bit line discharges. NOR cells are very fast. NOR cell based ROMs are very fast because there is just one NMOS there. But the problem is that they're not as dense. So we go to denser class of ROM memories, which are NAND memories. Now over here, we connect word lines. So we make a NAND kind of a structure. The topmost NMOS gets a clock, and the lower NMOSes get word lines. Okay. Now, suppose I want to read word line 0. I will keep word line 0 at low level. And I will, or wait, if I have to read word line 0, I will take word line 1 as 1, and I will maintain word line 0 at low level. Okay. So when the clock comes, what happens? When the clock comes, what happens? Will the bit lines discharge?
Wordline 0 के drain तक discharge होगा.
Yeah. So the bit lines will not discharge. है ना? The bit lines will not discharge simply because word line 0 is off. Now, if I do the programmation over here, and the programmation is something like this. So when I keep word line 0 at 0, which columns would discharge? What would I read? Are you able to see this? Hello?
So it is basically an NMOS stack completely, complete NMOS stack.
Yes, we have bypassed the NMOS through the programmation. We've connected the source or drain of the NMOSes where I wanted to write a 0.
Sir, and this connection should be dynamic, right?
Dynamic means?
I mean, it should be changing depending on the values which we want, or the select lines which we
Yeah,
get.
so this programmation has to be done by the user. He says, I want to store this particular code in the ROM. I would know where it is a 0, where it is a 1, and I will then appropriately put the connections there.
Okay, sir.
So if I say that I am reading word line 1, so I will keep word line 1 at 0. I will take word line 0 high, and then I will bring the clock in. So what do I read over here? Are you able to see this?
So can you repeat this part again?
So when I wanted to read word line 1, I will keep word line 1 at 0.
Yes, sir.
Word line 0 goes high, and
Yes.
clock goes high.
Yes.
What do I read? Now, even though word line 1 is 0, there is still a current path in this.
Yes, yes, yes.
I read 0 there. Now, because word line was 0, there is no current path here. So even though there is a current path here, and there is a current path here, I read a 1 there. Is that fine?
So how am I reading a 1 there? There is no current path in the third column, right?
Is there a path in the third column? My word line 1 is 0.
Yeah, there is no one. Yeah. Yes, sir.
Okay. So I read 0011. So that is how ROM cells are designed. It is not that you just connect or program on source side or drain side and nothing would happen. You have to be very aware of the impact that your programmation can have on the overall robustness of the ROM. Okay, ROM cells are very dense. See, instead of 6 transistors of a memory cell, you have just 1 transistor per memory cell. है ना? So ROM cells are very, very dense, which means that there are huge coupling capacitances that will come between these bit lines. There are many other additional variables that can appear when there is a particle strike or anything, and that can really bother you. So you want to keep as many things in control and fixed. Even if that means larger power consumption, fine. Even if that means a little higher delay, you would say fine. But at least it is deterministic. It is in my control. Because there are so many other variables which will come into picture on silicon which are not in my control. So you want to keep as many things in your control. So you prefer to do source programming on the NOR ROMs than the drain programming. Okay.
So, for example, so you were saying that the bitline capacitance would obviously the interbitline capacitance would be significant because it is denser. But so, for example, if I'm storing a 0 here and it's going to 0, and on the other side I'm going to store a 1, but since I don't have a connection there, so why would that be worrisome for me?
Because there is coupling happening between the 2 bit lines. Huh? These 2 bit lines will couple. So you had assumed that this bit line will not fall.
Yes,
It assumed it will remain at VDD. But due to coupling, it falls.
So, but where's the path to fall? I mean, still they need a bit.
Coupling हो रहा है ना, Raghav? What happens in coupling?
Okay.
What happens in coupling?
So I mean the capacitance kind of other capacitance will try to.
Yeah,
take
2
it in.
wires were running close to each other. You take one wire to VDD.
Yes, sir.
What happens? You see the other wire also starts to rise a bit. That is what is coupling. Over here, you are discharging one of the bit lines to 0. So the other bit line, which was not expected to discharge, it's a floating capacitor, it will also discharge a little. It was supposed to be like this.
Okay.
Okay. So with ROM, you have to be extremely careful. ROM designs are not simple. It may appear that, oh, there is no right circuitry, so I have to design lesser circuits. But the circuits that you have to design are so dense that you have to be extremely careful that they remain functional even in the presence of these crosstalk and other capacitances